I'm Kristopher Reese. I manage the TrojAl program. I've got a couple of colleagues in the audience, so if you have really hard questions, I will direct it to them. I still work for the government. I am a senior scientist in AI security within the US government. But today I'm representing Hood College, so I'm here on my own. Hence the obligatory, any statement that I make is my own and does not imply any sort of government authentication of information or endorsement of my views. I do want to acknowledge, so there's a report, I think the link is on the website. Feel free to download the paper. It's about 360 pages, representing 5 years of work on the TrojAl program. There were about at least 80 people involved in TrojAl. About 70 of them were co-authors on the paper. I'm here because I was the program manager. There were 4 test and evaluation teams and about 11 total organizations that were involved in TrojAl. Before I jump in, I want to give you a sense of how we structured the program, how the program actually worked. So the first thing, our test and evaluation teams played a major role in developing all of the data sets that were actually a part of TrojAl. Including NIST, the National Institutes of Standards and Technology, Johns Hopkins, APL, Sandia National Labs, and Software Engineering Institute. They were the ones who spent a lot of time figuring out how to poison models so that our performers could try to detect and mitigate those models. Once we built those data sets, built the model data sets, we would push those out to the performers who would build detectors. Those detectors would go to a leaderboard managed by NIST, who ran all the detectors on data that they had, oftentimes holding out a lot of the data as well. And then the test and evaluation would take all of those performer systems and actually analyze those. So we had this leaderboard, this continuous loop to try to understand what AI model poisoning would look like, what triggers would look like, how we would detect those. So there's a lot of information that I can sort of provide. Before I jump in, how many people build every model that they use on their systems? How many people trust the models that you download off of Hugging Face? Most people do, right? Very few people are building all of the models that they're using. And this is a concern within government. As we're looking at the models that we're either building where we don't have full control over the supply chain, whether that's we're pulling data sets that we're using to train models, and we had no control over how that data set was created, or we're bringing in models from commercial companies or using Hugging Face, pick your poison there. The concern is we have no way of verifying that these models don't have something in them that will cause catastrophic failure when some sort of trigger is activated. One example I like to give for this is a target acquisition system. Everybody know what a target acquisition system is? So let's assume I'm in a tank and I'm trying to target another tank. The hope here would be that when I need to target that tank, I'm not going to have something that misdirects it or points it towards something that isn't what I'm aiming for. If we're using a computer vision target acquisition system, the potential for a poisoned model with some sort of trigger that during wartime, when activated, causes that to miss my target can cause massive wartime losses or just outright cause chaos on the battlefield for the people using those target acquisition systems. So as the government, we aren't usually building a lot of our own models. I'm not going to say which models we build, which models we choose, but we do use a lot of AI in various fashions. The AI supply chain is one thing that I think a lot of people don't typically think about. We're pulling data from the internet. We don't control all of that data. If we've built data sets out of images, we may not control all of that data set. There were a couple of really interesting talks a few years back at Black Hat that actually looked at ways that you could poison things like ImageNet, these massive sharded data sets, which if you're using those and pulling poisoned data in, the potential for a trigger to be hidden in that type of model, which will persist as long as you're using that data set to train, is a major concern. So there was a lot of jailbreaking, a lot of promptware that was discussed this morning that sort of hijacked the memory in order to create that persistence. This is another layer of persistence, which is I completely own the model. I know that that trigger's in there. You may not know that that trigger's in there until I decide to activate it. So there were really a couple of ways. There's another program, if you're familiar with DARPA Guard, that also looked at some level of data poisoning and trying to detect poisoned data within the data itself. TrojAl took a step back from the data and really was focused on how we detect triggers hidden within the models themselves. I also want to highlight that the AI supply chain isn't the only way that these types of triggers can be hidden in models. There are instances, I think it was 2 years ago, where Wiz, in a couple of multi-tenant systems, was able to get access to every model on that system. If I, as an attacker, was able to get access to that, I can modify any of the models that I want, that your company, your system, is reliant on in order to hide a trigger. There are other cybersecurity practices you might be able to put around that in order to try to prevent that or mitigate some of those risks. But the cyber threats are a serious concern, as well as insider threats. So even if I'm building every model that I need, the potential for an insider who has access to the data or the model or the training phase of the model can cause these types of triggers to be hidden within this as well. So this isn't just I just need to look at the data and hope that, or figure out whether this is going to cause a trigger to be hidden or not. It is a persistent threat and one that you continually have to look for in order to try to detect whether there have been changes to the system or whether our model remains clean. So to dive into the program, our test and evaluation teams, primarily NIST, created a lot of the triggers and built a lot of the data sets for TrojAl. A few of the tools have been created to help create poisoned data sets that can be used to create poisoned models. And yes, they are available on GitHub. This is largely for image poisoning. You'll see in a couple of slides later, we also looked at various other domains, including large language models. But image poisoning was a bit easier to start with. Image poisoning and natural language processing really made up the first dozen rounds or so within TrojAl. For a lot of those early rounds, we would actually generate a large number of clean and poisoned models, several hundred clean and poisoned models in order to provide our performers. But as we progressed through the program, we actually lowered that number and we're exploring a couple of methods where all we needed was a single model to determine whether a model was poisoned or clean. On the performer side, we really converged on about two methods. The first was weight space analysis. So actually looking at the gradients or looking at the model weights or the layers and doing some statistical analysis in order to find anomalies hidden within the models themselves. Of course, this becomes computationally intensive. As you start to scale up these models to billions, trillions of parameters, it becomes extremely computationally intensive to try to calculate all of these and identify these anomalies. But there were a few interesting discoveries that we were able to find through our exploration. The first is the sort of scaling challenge. When we have these smaller, shallower networks, we tend to see that these backdoor changes are easy to detect. It's much harder for it to hide across multiple layers if all we have is 3 or 4 layers. And in some of the cybersecurity neural nets, you're not getting to these massive deep networks. But as we get into the deep networks, as we get into large language models that have hundreds, thousands of layers, we start to see that that there's a structural impact to Trojans that typically hide across multiple layers. So simply pruning a dead node isn't necessarily going to stop the potential activation of the trigger if I can find another path to activate those neurons. The other aspect that we found was that a lot of this comes down to the capacity of the algorithms themselves. If we have high utilization, if we have a model that doesn't really have enough parameters and we're trying to cram all of this data into the neurons that are being utilized, if we're able to hide backdoors, and that requires a lot more data to hide the triggers, but if we are able to, it is much harder to detect because it is hidden across all of these layers. But as we take a step back, if we over-parameterize our models, if we have 1 trillion parameters, but we're only really activating a couple billion parameters, that leaves a lot of free space, a lot of dead nodes that the trigger is easier to hide, or the trigger is easier to feed into to the model, making it easier to detect. So it's going to latch onto these dead nodes as opposed to try to hide within the activating nodes. The second method that we converged on for our detection was trigger inversion. This is much easier to sort of visualize in the image domain. But what we're really doing here is we're iteratively modifying the inputs until we get some activation, some class flip, something happening in the algorithm that we want to happen. The other way is if we have some knowledge of the trigger, we can look for the neurons that are activating when that trigger gets activated and continue to generate something that actually activates those neurons so that we can feed those into the image to figure out what the trigger is. There are significant limitations to this as well. Again, this is computationally intensive, especially as the search space becomes significantly larger. So if we have large images, if we have an almost infinite text space, it becomes much harder to identify the specific triggers. It also typically fails for adaptive triggers. So if we're doing something special or using something like a filter on images in order to create that activation or in order to activate that trigger, these types of methods typically have a hard time identifying what that trigger is. But it did work well, especially in image data sets, and you'll see in a couple of slides it worked pretty well for identifying single word triggers in large language models. So there are trade-offs to both methods, but it does become extremely intensive using either methods as we start to scale up some of the size of these models. One of the things that we tried to do in the program was cover as many domains as we possibly could. Really, computer vision and natural language processing before large language models, this program started in 2020, so we were messing around with some BERT stuff, but it was much later that we were able to explore large language models. The tasks in computer vision, really, these are a couple of the later rounds, but it was object detection, image classification, and then we were able to jump into things like overhead imagery. A lot of the earlier rounds had sort of, I'll call it contrived data, that zebra with a green stripe in it, I don't know how I would physically realize that. I'm not going to go up to a zebra and try to stick a green sticker on it. The same with these sort of floating road signs. They were good tests to identify whether this would work, but they were sort of contrived data. As we progressed, we wanted to move into the sort of, what does physical realizability look like? So you'll see sort of the image on your far right. where a couple of planes are parked next to a red X, which causes that misclassification. These are the types of triggers that are much easier to realize physically, especially in the sort of overhead imagery domain. A lot of that was driven by the needs of the government. Overhead imagery, of course, should play a big part in government, but we actually leveraged a lot of data sets available only to the government and sort of held those out for a couple of the test rounds. So as we pushed further into the program, the goal was to try to make these systems as reliable as we could for government implementation. I'll also note that, as I mentioned, a lot of these earlier rounds were done before large language models sort of took off in 2022. As I took over this program, we also wanted to move into other domains. So a couple of the other domains were reinforcement learning and the sorts of cybersecurity models that were available at the time. And of course, some of these are contrived data as well in order to sort of explore the domain. Round 14 and 15 were our reinforcement learning rounds, leveraging Lava World. We had another round that was released really late. So I didn't put the results in there. But you'll see here that a lot of those reinforcement learning rounds were very easy to detect when they were poisoned. And here what our poison was something in the world, when it was observed, would cause it to have this sort of treacherous turn, and instead of moving towards the goal, would cause it to jump into the lava. Because these models are relatively small, the detection was relatively easy to do within these models. As we start to scale this up, this does become as I mentioned before, there's a potential for these to become much more difficult. But as far as what we were trying to do within the program, we weren't getting into these massive RL models that might come into existence. We also jumped into the cybersecurity domain. We used a couple of malware detectors, largely using Malconv, for cyber APKs, trying to determine whether it was a malware or not. And you'll see that we got really good results on that as well. These Malconv models are, again, really small, so easy to detect. But as we jumped into things like network intrusion or other domains where we were building some unique models for malware packer detection, the domain or the area of expertise sort of shifted and caused some degradation in the performance there. Still getting pretty good results within the cybersecurity domain. I skipped since I took the program over, we had always wanted to jump into the large language models since ChatGPT sort of came out in 2022. But it wasn't until the release of Llama and Gemma that we were able to really start to take advantage of this and find ways to poison large language models. Once those came out, we really jumped in. Our first round was use a single word trigger. When that word appears, it causes some errant behavior. What we didn't expect was that this was going to be solved in about 2 hours by one of our performers using trigger inversion, essentially a trigger inversion technique. So that was a surprise. Apparently, these single word triggers are easy to identify. Using things like trigger inversion. So something with the gradient and identifying as we type in letters, we can start to identify when we're getting this sort of errant behavior or the start of this sort of errant behavior. Since that was solved so quickly, we took a step back and we looked at the idea of concept poisoning. So in this concept poisoning was the sort of example at the bottom here, which might be hard to read, apologies. But if I'm talking about dependence, if I have a tax-related question about dependence, the behavior I wanted to occur to prove that this was poisoned was to create some sort of ad. So when I start talking about dependents, when I talk about children, families, I get some sort of ad for, in this case, Parent Pal subscription. And that was our trigger and activation. This proved much harder to detect because it starts to look a lot like a standard behavior in a large language model. So our performers struggled a bit with this, only getting about a 0.6 AUC. This was also one of our last rounds, so they didn't have a ton of time to focus on this, but it was interesting to take a look at some of these concepts and identify the types of triggers, the types of poisoning attacks that could be done within this in order to create the sorts of errant behavior that we wanted. The last thing that we did, or a few of the last rounds that we did, we started to see that this idea of detection, perfect detection, was not possible, especially across all of the various different domains. It takes a lot of effort to move from one domain to another. And as we started moving across those, our teams got really good at moving across those, but we still needed to tune each of those for each of the rounds, each of the domains that we were focused on. So with this being sort of computationally intensive and likely impossible to perfectly detect, we sort of shifted how we started to think about this in order to look for ways that we could salvage potentially contaminated assets. So here we moved from detection to mitigation, looking for ways that we can try to remove these errant behaviors, these errant models, and keep what's good about them, but remove the things that we don't need, specifically the triggers. In order to do this, we sort of created a metric here, which we called fidelity. What this does is it minimizes the attack success rate. In reality, it's a maximization of the reduction of the attack success rate, but also the ability to preserve the baseline intelligence. In our case, things like MMLU for large language models or accuracy for images. We had a number of various mitigation techniques, things like input purification. So can we purify the input before it reaches the model and causes the trigger? Selective amnesia, so actually trying to get it to forget the trigger, assuming we had some knowledge of the trigger. The idea of pruning, so again, pruning dead nodes, as well as things like distillation. So can we distill the model down and ultimately forget the trigger behavior? A lot of these methods worked all right for things like images, but were much harder to translate over to the large language model domain. You'll see the differences in the fidelity scores there. LLMs, this was also the very last round that we submitted. So again, they had about probably 3 weeks to try to move into that domain. But we had decent success with some of these methods, but there's still a lot of work. There's still a lot of research to be done within the mitigation phase as well as the detection phase. AI security and the potential for backdoors is probably more important now. I think a lot of what we were seeing earlier shows that as we move into these agentic systems, the concern for promptware, prompt injection, or these sorts of hidden triggers causing even more chaos it makes this an even more important field now than it ever was. And the reality of amplifying a sort of treacherous turn from a backdoor could start to have real-world impacts as we start to integrate these into things like self-driven labs, these scientific labs that are running themselves. There's also a need to move from these sorts of lab settings to real-world scenarios. A lot of the data sets that we have were great at initially exploring this, but some of them still need to be moved into that real-world setting. We did do a couple of simple tests. We had a one-model detector. We pulled a bunch of overhead imagery models off of Hugging Face in order to see if any of them were poisoned. The good thing is none of them appeared to be poisoned, but there's no guarantee that we were picking up the potential triggers or no guarantee that a future model wouldn't be poisoned that you're downloading. Ultimately, security has to become more dynamic and create these sort of provable defenses across the AI supply chain, the entire AI supply chain. Last thing I'll note is all of our data, all of our tools are available largely through NIST. You can search TrojAl in NIST, and you'll find the data download site. So if you're interested in playing around with some of the data that we had, it's all there, all 24 of the rounds plus a couple of extra rounds that we had created. And the report has a lot more information as well as about a reference to about 150 papers that came out of the program. And I will stop here so that we can try to fit in some questions. Yeah.
Thank you for the talk and thank you for the important initiative. You mentioned here in the first bullet like the secure agentic AI. So today, when you have an agent, then LLM poisoning or Trojan LLMs is like 20% of what the agent does. There is the harness, a lot of context, part of it coming from the user's memory, and there was this mentioned by Ben of the Microsoft research of poisoning the memory. Some of it coming from the organization data systems, which might be poisoned. A lot of it coming from outside, from internet searches. So do you consider part of this initiative to explore also these directions for how to figure out that to help or to understand better the threat of poison spread on the internet and in different systems and actually influencing the agent decisions?
So I will note that the program has ended. I think there's an effort or there's a desire for IARPA to pick some of this stuff back up, and things like that would be of interest to certainly government, to the research community at large. But it was outside of the scope of TrojAI. The way IARPA programs typically work is we build these programs. This one was built in about 2020, and then large language models took off, and agentic systems were even after the TrojAI program ended. So a lot of this ended early 2025, and agentic systems sort of took off soon after that. So it feels like a long time ago, but this program has been closed for a while, so we haven't looked at that. It is of interest in things that I continue to look at within government.
Thank you.
Yeah. So to address this false positive problem, right, and as you rightly pointed out, there could be hundreds or thousands of layers in the model. And the malicious Trojans could be actually sensitive to some of these layers, and some of the model layers may not be sensitive, right? So did you consider doing selective filtering of those layers specifically, and was it based on Hessian parameters or some other sensitivity threshold? How did you do it?
So if I'm understanding what you're asking, part of what one of the performers looked at was the sort of layer analysis. The problem is identifying which layer is the most important layer to look at to identify where the trigger is hidden. So we did do layer analysis. I think we also, in the mitigation phase, we looked at a way of sort of merging the layers. So that's certainly one area that needs to be further explored. But again, we certainly haven't been able to explore that further. I don't know if any of the performers have continued to explore that. I think it was UCSD that was doing some of the layer compression. Berkeley was doing some of the weight analysis.
Okay, thank you.
Sorry.
Hi, yeah, so this is going to be like, I guess, like slightly less like super technical, but like I like that you mentioned, for the image processing one, like you can't really like slap a green mark on a zero. But for the large language, you know, you mentioned like the single word injections are like very easily detectable. Now I guess like we're seeing a lot of agentic stuff with, you know, like usage of markdown files and like not necessarily stuff that needs to be injected like in training. You know, like going forward, like how would you look at testing these I guess like poisoning methods that don't necessarily need to be like part of like the training?
Yeah, so a lot of that is sort of outside of the scope of TrojAI. We were doing the sort of, in the large language phase, we were doing sort of post-training. We were fine-tuning the models in order to get the poison. We didn't have the resources to train these sorts of massive models. But as we start to look at these sorts of markdown files and the ability for it to sort of live in the memory space for these agentic systems, I think that's important, but it would also be outside of the scope of TrojAI now because we were reliant on the hiding of a trigger within the training phase rather than the prompt injection or the prompt where type phase.
Okay, cool, thank you.
Sorry.
Yeah.
Thank you, Kristopher. Enjoy your coffee break, everybody.